Earlier this year, on the 9th of February, an Atlas V rocket was scheduled to launch from Cape Canaveral in Florida. Its cargo, the European Space Agency's Solar Orbiter. A spacecraft with a decade-long mission to explore our sun.
Welcome to the Kennedy Space Center as we celebrate the upcoming launch of Solar Orbiter.
And our cameras were there to capture the whole event.
Simon Winchcombe, BBC Sky at Night. After all the hard work, how do you think you're going to feel when it finally goes off?
I'm pretty sure I'm going to feel amazing, to be honest.
You are looking at a live view of a Solar Orbiter mission.
This evening, we're going to find out just what Solar Orbiter's mission is and what it hopes to discover.
T-minus 10 seconds. 9, 8, 7.
Welcome
6,
to the Sky at
5,
Night.
4, 3, 2, 1.
For solar physicists, it's an exciting time to study our local star. Late last year, the DKIS telescope in Hawaii took these remarkable images. Huge convection cells of hot gas seen on the surface of the Sun, and each of them the size of Texas. And, after launching last summer, NASA's Parker solar probe is sending us valuable data about the Sun's magnetosphere. And we'll be finding out just what that's telling us later in the program. But tonight, we're looking at ESA's new probe, Solar Orbiter. In the run-up to the launch, we spoke to many of the engineers and scientists who've designed and built the spacecraft. A spacecraft that is now on a 10-year journey to the heart of the solar system. Its mission, to answer fundamental questions about the Sun. What drives its awesome power? And can we predict its behavior? But first, we hitched a ride with Lucy Green on her way to the launch site. And she revealed how the Sun influences us beyond its heat and light.
It's not called the solar system for nothing. The Sun absolutely dominates. It dominates in terms of its gravitational field that keeps everything in orbit around it, planets, asteroids and so on. But it also dominates because the Sun's atmosphere is actually blowing out into the solar system in something that we call the solar wind. And that takes particles, plasma and magnetic fields out into the solar system as well. And the huge bubble of gas and magnetic field that it creates is what we call the heliosphere.
The heliosphere defines the extent of the solar system. Within that space, the Sun creates solar wind and space weather, solar storms and coronal mass ejections.
Solar storms are what I think is one of the most exciting aspects of how our Sun operates, and solar storms are comprised of two things. One is that we have explosions in the atmosphere of the Sun that we call solar flares. They eject high energy radiation like X-rays into the solar system, but we also have eruptions that we call coronal mass ejections. coronal mass ejections and large flares are sort of beams of high energy particles, so electrons, protons, that get accelerated out into the solar system and travel the 150 million kilometres from the sun to the Earth in maybe half an hour or so.
Because coronal mass ejections can destroy communication satellites and power grids, predicting them is critical. And although we know the basics of solar storms, they aren't completely understood. And there are also other mysteries. First, the extreme temperatures in the outermost layer of the sun's atmosphere, the corona.
The surface of the sun has a temperature of around 6,000 Kelvin, 6,000 degrees, and the atmosphere of the sun has a temperature of a few million Kelvin. And we know that the magnetic field that threads through from the surface up into the atmosphere, into the corona, is probably key to understanding that massive temperature hike, but we don't know the details. Another area is looking at the origin and the evolution of the sun's magnetic field itself, something that we call the solar dynamo. And the sun's magnetic field is really at the heart of everything it does. So it's at the heart of eruptions and explosions in the atmosphere. It's at the heart of space weather. And so we really need to know in more detail how the magnetic field is formed in the first place. How does it evolve over time? And I love the kind of irony that we have designed Solar Orbiter to withstand certain conditions. In fact, we don't really know exactly what those conditions are going to be like. That's what we want Solar Orbiter to go and study.
Continue on the current route.
For Lucy, the launch of Solar Orbiter comes after many years hoping for this moment.
My first involvement with Solar Orbiter goes back to 2005, and I remember thinking, what kind of spacecraft would we need? What instruments would we need on board? What cameras? What detectors? It feels slightly surreal, actually, after all these years, to be finally driving towards Kennedy Space Center, knowing that Solar Orbiter is in the fairing of the Atlas V rocket and is on the launch pad. I just can't quite believe it after 15 years of knowing, wanting, thinking about Solar Orbiter, that it's finally going to happen.
You are about a quarter of a mile from your destination.
Solar Orbiter took almost a decade to be built. Hours of thought, dedication, and plain old hard work. The next step is to launch it beyond the Earth's gravitational pull towards its destination. And it will be an Atlas V rocket that does that job.
My name is Scott Messer. I'm the program manager for our NASA Launch Services contract. I get the excitement of launching and being part of all of the missions that we launch for the NASA space agencies. The Atlas program started back in 1957. It's had 664 launches since that time. But the Atlas V, launching the first time in 2002, has been 100% successful for every one of its launches, and it's a highly reliable launch vehicle. We do not go until the spacecraft is ready and the launch vehicle is ready and everybody's comfortable. Doesn't really matter how long that takes. Mission success is our top priority for all of our customers. The rocket stands about 189 feet or 60 meters. It's 4 meters in diameter. The configuration of the vehicle that we're launching for Solar Orbiter is known as a 411. It's got a first stage, a second stage, and one single solid rocket booster. A single solid rocket booster is a little unique because The vehicle is not symmetrical. A lot of people wonder about that, but the engines and control system are canted in order to account for that and make sure it flies successfully.
The rocket's planned trajectory, like every other launch from the Cape, is to head out over the Atlantic before separating from its cargo and falling into the ocean.
After about 2 minutes, we burn out the single SRB. Roughly 4 minutes into the flight, the first stage will separate from the second stage. Then there is a burn of the second stage, followed by a 30-minute coast around the Earth, and then another burn right before separation.
For Scott, just like every other launch, Solar Orbiters will make his day.
It is absolutely exciting, and particularly when we get down here to the launch site and we're just about ready to launch, and I get to work with the spacecraft builders a little more closely. It is super, super exciting.
Minus 15. Roll for ignition.
ESA's Solar Orbiter is not the only mission studying the Sun.
5, 4.
Just over 18 months ago, NASA's Parker Solar Probe took to the skies.
Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe. A daring mission to shed light on the mysteries of our closest star, the Sun.
Parker's already travelled closer to the Sun than anything has before. And today, as it's still sailing into its final position, it's already transmitting data in an attempt to solve a puzzle that we don't quite understand.
I am Nikki Fox, and I am the director of NASA's Heliophysics division. I love my job. That's one of my hashtags. I love my job. We know the Sun is a variable star. We've also known for well over a century that the corona is 300 times hotter than the surface of the Sun. It doesn't make sense. If you walk away from a campfire, you don't suddenly get 300 times hotter. So what is causing coronal heating? We know that the magnetic field is really key. It is twisting, it is compressing, it is getting suddenly stronger and then releasing this energy. But we've never been able to truly answer that question because we've never been able to go close enough.
By getting closer to the Sun than ever before, the Parker probe is attempting to find how the magnetic field causes this heating. And it's already making discoveries. Magnetic structures the science team calls switchbacks.
So Parker Solar Probe, even on her very first trip through the corona, saw things that we didn't expect. And by that I mean suddenly we saw all of these sort of reversals in the magnetic field. At first we thought, well, maybe we're on the boundary between fields that come from one pole of the Sun and fields that come from another, and they actually have magnetic field lines that would be in the opposite direction. But when we added the plasma data, we actually saw, no, actually it's not reversing in direction. The entire field is wrapping back and forward. It makes like an S shape. And so if you think about taking a thick rubber hose and trying to twist it, it's hard to do it. You have to put a significant amount of energy to get that twist in the magnetic field. They're putting a lot of energy out there. You have a lot of them all over the place. You're now heating the corona. And so we've seen this sort of smoking gun.
It seems the release of energy from the switchbacks is heating the corona. But what's causing the switchbacks themselves? It's suspected that plasma coming from the poles is key to understanding these switchbacks. But Parker's orbit doesn't take it over these elusive regions, and so it can't study what's happening there. Solar Orbiter's orbit, though, will.
So the big question for us right now is why? Why do we see these switchbacks? I think the poles are going to be very, very exciting. I think we're going to see things that we have never seen before. And I think we're going to find an awful lot of physics is actually driven by what is at the sun's poles.
Daniel Muller has been working on the Solar Orbiter project for over a decade.
And in total, effectively, almost all European countries plus the US have been involved in making this come true.
It's part of his job to get the spacecraft where it needs to be to study the sun.
These are all my children. I love them all equally. And the great thing is they work even better as a team.
This project has been a long time in the making, and I've been personally involved since 2007 in an early study phase already together with NASA. And in 2012, I took over as the project scientist for the mission.
The most important thing is that this is really an endeavor that makes borders.
This is really an amazing international effort. It's been frustrating at times, but we've really overcome the challenges, and I think the team has really pulled together.
The first aim of the mission is to get Solar Orbiter closer to the sun. But because of the sun's vast mass, this is not an easy nor a quick thing to do.
The challenge about Solar Orbiter's orbit is that we actually need to slow down rather than accelerate. If you want to go all the way out to Jupiter or Saturn, you just go and you use the planets as a slingshot to get you further away and faster. While what we want to do is we want to get closer in and therefore have to slow down. And it's hard to break in space, so we try to use the momentum, the gravitational potential of Earth and Venus to accomplish that. They provide us with more energy than we could ever use the thrusters for to change the orbit. And so we need to really fine-tune our initial trajectory to hit Venus just at the right time. And in a way try to fall more to the center of the solar system. Getting closer to the sun, getting better pictures.
But slowing down to snap the closest ever pictures of the sun won't be the orbiter's only trick. Because it will investigate something never seen before. The interaction of the sun's poles with its magnetic field. So Solar Orbiter's journey will allow it to take the first ever images of those regions.
With Solar Orbiter, we hope to find out more about the global magnetic field of the sun, how it shapes the entire interaction between sun and Earth, because the magnetic field provides the pathways for the particles to travel. And we have become relatively good at modeling the large-scale magnetic field, but where the data ends is really the polar regions. So this is really terra incognita, and this is why we want to fly out of the ecliptic to look at the pole.
But this unique journey to study the poles will take over 5 years.
Every few orbits will meet Venus again and use its gravitational potential to slingshot out of the ecliptic plane. And then every 2 years or so we will raise the inclination by a few degrees, so that around end of 2026 we'll ramp it up from 17 degrees to 24 degrees out of the ecliptic plane. And that is a decent angle to actually see the sun's poles for the first time.
Solar Orbiter will pass within 40 million kilometers of the sun. And that will generate temperatures of over 500 degrees Celsius on its surface. And so the spacecraft needed a special protective coating.
One night reading a book called Titanium and Medicine, I got this sort of a eureka moment. Said, I have to try that. My wife wasn't particularly enamored with my eureka moment, but there you go.
The eureka moment was a new method of creating metal coatings.
I came up with this concept for using grit blasting as a technology to remove oxides off metal and to put something else on once the metal is denuded and very, very reactive.
A suggestion to ESA that this technology may be of some use was well timed, because they were designing Solar Orbiter's heat shield. and they believed the new method, called co-blast, might be the answer to protect the craft from the intense heat of the sun, by absorbing sunlight and then allowing it to radiate back into space.
All of a sudden, they came to me and said, can you put a black material down with co-blast on the surface of titanium? But it also had to be non-weight additive to the heat shield. It had to be conductive so that you don't get static pooling on any component on the craft. It had to be non-shed because you don't want material getting on the lenses. It had to be such that it doesn't degas. The key thing is that, you know, the beginning of life and end of life, it couldn't fade over the 7 to 8 years in operation. We looked at several different materials to try to put a black, you know, absorbative, emissive, thermal control type surface on titanium, and they all failed. And I was quite desperate. Then had another eureka moment. I had read when I was a kid, you know, Encyclopedia Britannica, somebody had said something about putting, you know, charred bone and charcoal as the sort of crayon material that they used for cave painting. We tried it, worked first time. So yeah, serendipity, luck, call it what you want, it worked.
The protective coating created from charred animal bone was named Solar Black. But other components were to be protected by
that you're the reason that the solar orbiter can launch. That's still quite unbelievable.
The Solar Orbiter spacecraft that carried the science instruments was put together by Airbus in Stevenage, but the instruments were built across 17 European countries. And managing those instruments as they come online and start sending data back to Earth is a complex process.
So I'm Annick de Groof, and I'm an instrument operations scientist. I'm one of the people who will coordinate the science planning. We have 10 instruments on board, but actually several of those instruments have several telescopes or have several sensors. So in total we have 27 telescopes and sensors altogether. The magnetometer actually consists of 2 sensors. SWA is the solar wind analyzer. RPW is the radio and plasma waves. EPD will measure the energetic particles. SOFI is the polarimetric and helioseismic imager. It's actually a very complex instrument and very, very interesting. EUI is the EUV imager. SPICE is the spectrometer. STIX is the X-ray imager. We'll see all the flares, even the tiniest ones. That's really a lot, yes, for sure. Because one of the reasons we have such a comprehensive suite of instruments is that we want to let them work all together to give really a very good overview of, on one hand, what's happening on the sun. And on the other hand, we also want to measure what's happening around the spacecraft. So we want the sensors to feel and sniff around the spacecraft what's happening in the solar wind.
In the hours before launch on the 9th of February, we caught up with 2 scientists who were intimately involved with 2 of the instruments. Louise Harrer on the Extreme Ultraviolet Imager, and Helen O'Brien on the magnetometer, or MAG.
MAG consists of 2 sensors. They're 2 magnetic field sensors. They weigh about half a kilogram each. They can sit in the palm of your hand. And we actually mount them on a boom which extends out the back of the spacecraft. So it measures the magnetic field in the solar wind that's thrown off the sun. The sun looks like quite a plain, boring disk in the sky, but actually the surface is incredibly dynamic. It boils and bubbles, and all these explosions happen on the surface of the sun. And those explosions that happen mean that the sun's atmosphere essentially expands out through space. It's very highly charged particles, And those are all mixed up with the magnetic field, and that's what we measure when we see the solar wind go past.
Although these explosions are violent, the changes in the magnetic field millions of kilometers from the sun's surface are minute. And so the instrument has to be super sensitive.
The fields that we're trying to measure are very, very small. It's so sensitive we could detect an MRI machine switching on from across the other side of London from our lab in the centre of London.
Then there are the best ever pictures of the sun's surface that Solar Orbiter is designed to take.
I'm the co-principal investigator of the EUV imagers, so they will allow us to see all the dynamics, the explosions that happen in the sun, and it's imaging in the way your smartphone would do, but what's special about it, it has special filters on it that allows you to see in this different wavelength bands in high resolution. And that allows us to observe where the solar wind is coming from, where the storms are coming from, and then measure that as it flows past the spacecraft. This is pure exploration. We don't know what we'll see, but we do know it will help us understand the sun and the sun's activity.
Good evening to those watching from here in the States, and a very good morning to our friends watching from Europe, as we kick off our coverage of the Solar Orbiter mission that will study the sun and capture, for the first time in history, images of its poles.
Ground. Go. Facility. Go. RFFTS.
Go.
Flight control.
Go.
GCQ. Go.
T-minus 10 seconds. 9.
At precisely 11:03 p.m. Eastern Standard Time, the Atlas V rocket was launched.
2, 1, 0. And liftoff of our solar orbiter, an international collaboration to give us new images and a better understanding of our life-giving star.
It's going to be some time before Solar Orbiter enters its planned orbit around the Sun, but we'll be sure to catch up with it when it does.
Watch the launch go of Solar Orbiter. It was just beautiful. It was so successful, like clockwork. All my colleagues here feeling a bit emotional now. We were able to watch the rocket go towards the moon, and then Solar Orbiter is on its way to the sun.
Successful flight that it has been so far.
Next month, Maggie and I were supposed to be touring telescopes in Chile, but events have got in the way. But we will be on air, even if we have to film here in my back garden. So until then, stay